So in this lecture we will continue our previous topic, that is intersymbol interference. In the last lecture we had seen that what is ISI, what is reason of occurrence of ISI. So ISI is occurring because a band unlimited signal is passed through a band limited channel. So to avoid that ISI, we used a solution, that is we made signal band limited from minus RB by 2 to RB by 2. So that was called, so the shape was like this. That was called Nyquist first criteria to have zero ISI, but that is called an ideal solution because of these reasons. So reason number one, this is impractical solution. Why? Because the pulse which was coming in time domain is varying from minus infinity to 0 to plus infinity. So it will take infinite time, and further it is a non-causal pulse because this pulse is occurring in the negative of time axis. And another reason was that if I have some jitter at the sampling instant, then ISI will again come into picture. So these are, because of these reasons, the solution which is given by Nyquist, the first solution which is given by Nyquist is ideal solution. So it cannot be implemented in practical. So question arises, what is a practical solution? So we will discuss Nyquist practical solution for zero ISI. So let us see how we can have practical solution. So if we concentrate on this second aspect, that is its sampling jitter is there, that is why ISI will come back again. We can remove this problem. We can suppose we have, this is the pulse PT that we got through Nyquist first criteria or ideal solution. So because of timing jitter, if I am sampling here, then this ISI is again coming back into picture. Now what if I have something which has low amplitude in these side lobes? This amplitude is high. So in the negative region, this amplitude is high. If I have low amplitude, if I generate a pulse, if I design a pulse, if I shape a pulse in such a manner that rather than having this side lobe, I have this side lobe, then what will happen? Even though I have a timing jitter, then the effect of ISI will be reduced. In other words, the situation is like this. This is present case. I'm sorry, both have become same in this case. So this is present case, that is Nyquist ideal solution. And now if I design something like this, then if because of timing jitter I sample here, then this particular sample value and this particular sample value both are different. So my first case is smaller than my second case. The amplitude in the first case is smaller than the amplitude in second case. This is the gist of Nyquist second criteria of zero ISI. So what I need to do is, I need to reduce the extent of side lobe of pulse PT, the pulse which was part of Nyquist first criteria. Now question is how to do that. Now the meaning of reducing the side lobe is as good as we are decaying the pulse before infinity. In Nyquist first criteria, my pulse was varying from minus infinity to plus infinity, and if I want to decrease the side lobe, then pulse will end before infinity. So what I mean to say, in other words, if I want this to happen in time domain, then in frequency domain I need to go for expansion. In other words, if I take the PF, if I expand the PF in frequency domain, the PF that was taken in the Nyquist first criteria, ideal solution, if I expand that, then definitely there is going to be compression in time domain. This is the working principle of Nyquist practical solution. This itself is the Nyquist first criteria. Now question arises how to do that. This is what is shown here. In the Nyquist first criteria, my pulse PF, that is pulse in frequency domain, was varying from minus RB by 2 to plus RB by 2. Now what if I expand this pulse over this? If I expand this pulse over this, and what is the maximum frequency I can expand? So F is RB. Maximum bandwidth I can have is, your transmission bandwidth I can have is RB. So what if I expand over minimum required? What is RB by 2 is the minimum required or Nyquist rate. If I expand this way, then definitely in the time domain of this pulse there is going to be compression. Compression means the pulse which are supposed to be end in the at t is equal to infinity will now end before that, and this is what is shown here itself. As you can see, we have a pulse in frequency domain. We started from the frequency domain, and over RB it is extended till over RB by 2 it is extended till RB, and the excess of bandwidth over RB by 2 till RB is shown by a variable which is Fx. So now we will define something which is called as a roll-off factor, which is R. So roll-off factor R is defined as the excess bandwidth over RB by 2 till RB divided by the minimum required, that is RB by 2. That is called as roll-off factor. Roll-off factor. This is what is shown here. So roll-off factor is excess bandwidth which is over RB by 2 till which is over RB by 2 till RB. So excess bandwidth, when it is starting from RB by 2, excess bandwidth is 0, and when it is till RB, excess bandwidth is RB by 2. So Fx will vary from 0 to RB by 2, and minimum required is the Nyquist rate, that is your RB by 2. So your roll-off factor is a ratio of Fx and RB by 2, and as Fx will vary from 0 to RB by 2, that is why roll-off factor will vary from 0 to 1, and your transmission bandwidth is your minimum required is RB by 2 plus excess bandwidth, which is Fx. So we can say that it is RB by 2 plus Fx can be written from here in terms of R and RB by 2. So that become R into RB by 2. So your transmission bandwidth become your RB by 2 into 1 plus R. This is your total bandwidth in case we choose a pulse that is called a Nyquist 0 ISI pulse, and the solution is going to be a practical solution, because now the pulse will decay faster depending upon the value of Roloff factor. So if we take Roloff factor 0.5, or if we increase above 0.5, or if we take 0.25, then depending upon the value of R, your decay of the pulse will be different. So as R increases, decay will be higher. When R decreases, decay will be less. Now the question is whether the pulse that we have selected this way, that is a pulse which is going above RB by 2, satisfies Nyquist criteria. What is Nyquist criteria? Nyquist criteria is this, that is Nyquist 0 ISI pulse must satisfy this criteria, that is PT equals to 1 for T equals to 0 and PT equals to 0 for T equals to plus minus NTB, where n is greater than 1. Now to prove this, because it must satisfy, the pulse that we have chosen in practical solution must satisfy Nyquist criteria. What is that practical pulse? A pulse is like this, that is from minus RB to plus RB. So this pulse, that is in frequency domain. This is a pulse in frequency domain. So question is whether this pulse satisfies this criteria is an important question. Now to prove this, what we have done is we have taken a pulse train. So del TB is a pulse train. TB indicates that this is a period of the pulse train. So it is like a COM function. So TB to TB, these pulses are occurring at these intervals. Now what if I multiply these pulses, if I multiply delta TB with PT, then what is going to happen? If I assume PT satisfies Nyquist first criteria, PT satisfies Nyquist criteria for 0 ISI, that is shown here. This is a Nyquist criteria. So if satisfy Nyquist criteria, then if I multiply this pulse with delta TB, then what is going to happen? In that case, my result is going to be delta T itself, because as per Nyquist criteria, PT equals to 1 for T equals to 0, and multiplication will yield delta T, and PT is equal to 0 for other values of TB. So if I multiply delta T with that PT, the multiplication in this region will yield 0. So what I do is I take Fourier transform of this side and Fourier transform of this side. Then PT has a Fourier transform of PF. Delta T has a Fourier transform with a COM function. So it has a Fourier transform 1 by TB for all values of n, delta F minus NRB. And this has a Fourier transform, that is 1. So in that case, what I can say is 1 by TB sum F minus NRB, that is equal to 1. Here this PF 1 multiplied with delta F del F minus NRB, that yields PF minus NRB as per property in the frequency domain for a transform. So this particular equation, so what I do is I can take TB the other side. So finally I get this equation. In other words, if I choose a pulse which satisfies Nyquist criteria in time domain, then it will satisfy another condition in frequency domain. What is that condition? It is this condition, that is sum of PF minus NRB for all values of n is varying from minus infinity to plus infinity, that sum will be TB, since TB is a constant. In other words, what is F minus NRB? What is F minus RB? What is, for n is equal to 0, what is this value? Is a PF. For n is equal to 1, it is a PF minus RB, that is a pulse which is shifted by RB in the right side. If I take n is equal to minus 1, then it is a PF plus RB, that is a pulse which is shifted in the left by RB. So if I sum them, then it must be a constant, that is RB. This is another criteria. This is another condition for having 0 ISI. And if I choose a pulse PF which satisfies this criteria, that is given by equation 2, then this pulse will have definitely 0 ISI. So this is another condition to have 0 ISI, and this is shown here itself. So what is done? What is this? This is PF. What is this? PF minus RB. What is this? PF minus 2RB. Similarly, if I plot this way, then we will have PF minus 3RB. In the similar way, we have here PF plus 3RB, and so on and so on. And if I sum them up, the result is going to be TB. And the important condition is that if the result must, if I want the result to be TB, a constant, then the condition, this condition must be satisfied. That is, PF minus TB by 2 is equal to TB by 2. That is, now if you can see that at F is equal to 0, this pulse is 0. At F is equal to 0, my first pulse is, so I'll repeat again. So at F is equal to 0, this is first, this is second, and this is minus second. I say that this is the first pulse, second pulse, and this is minus second pulse. So at F is equal to 0, the first pulse is maximum, and second pulse is 0, and minus second pulse is 0. That is why the sum of all pulses is TB. Now this pulse, first pulse is decreasing as F is increasing, first pulse is decreasing, second pulse is increasing, and minus 2 pulse is decreasing. Minus 2 pulse is of course 0 after that. Now at this point, my first pulse is at F is equal to RB by 2. My first pulse is having the magnitude TB by 2. At F is equal to RB by 2, my second pulse is also having the magnitude TB by 2. So the total magnitude at this point is also TB, which means this condition is important to satisfy Nyquist criteria in frequency domain. This is a one of such pulse which satisfy Nyquist criteria for 0 ISI in frequency domain, that is PF is equal to 1 for mod of F less than equal to RB by 2 minus Fx. Fx is your excess bandwidth, and it is for this condition and 0 for this condition. And here we have shown this pulse for different values of R and its inverse Fourier transform. So here the pulse PF for different value of R, and here we have shown its inverse Fourier transform PT. So when R is equal to 0, which shows that there is no excess bandwidth. So this is your RB by 2, and this is your RB, and this is your PF. So when R is equal to 0, so my first case is for R is equal to 0, that is when there is no excess bandwidth. And when I say R is equal to 0.5, which means that from RB by 2 to RB, this particular range, 50% of range is this, that is RB, that is for R is equal to half. So in this case I will have something like this, and when this is your second case, that is when R is equal to 1 by 2, and when I say R is equal to 1, that means I am covering 100% of this range, that is RB by 2 to RB, 100% of this is covered, so it will go till this. So actually this meeting point has to be same, it is not drawn properly here, this meeting point has to be same, so that is point 3, so 3 corresponds to R equals to 1, and the same is shown in this diagram as well. But here you must take care that the meeting point of this curve has to be same, which is not drawn here properly. Now this is in time domain how this pulse will look like for R is equal to 0, 0.5 and R equals to 1. So here it is important to see that for R is equal to 0, if you see this particular curve, then it is like this, okay, and if you see for R is equal to 0.5, it will be something like this. So your side lobe amplitude is less, and if you draw for R equals to 1, so I'll need to draw again. If you draw for R equals to 1, then it will be something like this. So this will be less, actually it is drawn, it has been drawn more, but it is to be less. So that is, it has 2 0 crossing for R equals to 1 case. So what is the gist from these 3 representations? So gist is that as we are increasing the value of R, then the width, the value of the side lobe is decreasing, and when value, this is what we wanted at the start of Nyquist criteria for practical solution, this is what we wanted, that the side lobe should reduce, because if we have some timing jitter, then still the ISI should be less. This is what we have achieved. So maximum reduction in the side lobe is there for R is equal to 1, for R equals to 1. However, for R equals to 1, I am using the maximum bandwidth, maximum transmission bandwidth. So that is I'm using RB. My maximum transmission bandwidth is RB. So the thing is, now we have to have some trade-off. What do we want? If I want to have very less effect of ISI, then I must have R equals to 1. However, for R is equal to 1, my bandwidth is more, and if I have R is equal to 0.5, my ISI is bit higher, but I have less bandwidth. So what is shown here is a special case, that is for R equals to 1. If I put this R is equal to 1 in the previous equation, what is previous equation? My previous equation is this. It is this equation, this one. So what if I use R equals to 1 in this equation, then this can be written as this, like this way, and your sine term, your sine function will change like this. By using some rearrangement, I can write this as, this can be written as this, or this, or this can be written as this. This is all is obtained by some rearrangement. So PF for R equals to 1, that is full roll off. I have rolled off my full pulse till RB, in that case it has become cos square pi f dB by 2. So what does this look like? What is the cosine function? This is my cosine function. And what is cos square function? The cos square function will be like this, okay, because no negative side. So that is why this function, and what is this? This is a direct function to RB, that is from RB minus RB2 plus RB. It is like this. So what is this? This is your PF. In what case? In case when R equals to 1. So what is this called as? This is called as a raised cosine pulse, or raised cosine spectrum, or raised cosine spectrum pulse. Why it is called raised cosine? Because your cos function has been raised by 1. That is raised cosine. Cosine factor raised. So no negative part, only positive part. So this all is a part of Nyquist practical solution. So I'll brief what we have done. First, there was ISI. Why ISI has come? Because we are passing a band unlimited signal through a band limited channel. This has caused the output pulse to be band limited. This causes pulse expansion. The pulse expansion is a problem because it causes interference with the succeeding pulse, and this is called as ISI. What is the solution? The solution is I cannot change the channel because channel is always band limited. So what I need to do is I need to make my signal band limited. However, for that Nyquist gave a solution, that is a pulse. He designed or shaped a pulse. This is called pulse shaping. I need to shape my pulse in such a manner that it passes without any problem through channel. That is why the topic is called as a pulse shaping. So what he suggested is you shape a pulse PT in such a manner that PT is 1 for t equals to 0 and PT is equal to 0 for other sampling instant. And he referred this to as a Nyquist first criteria of 0 ISI. This was a problem. In that solution there was a problem because that is ideal solution. Why? Because this pulse is going till infinity, and the second problem is that it is not decaying fast, and if I have some sampling jitter, then my ISI will again come back into picture. To avoid that, we had some practical solution. In practical solution, what we did is we suggested a pulse with different roll-off, that is a pulse with a PF more than RB by 2, and in that case I came across a time domain pulse like this as is shown here, and for R is equal to 1 we got a raised cosine spectrum. So this way ISI can be reduced. However, there is some disadvantage of Nyquist practical solution as well. The disadvantage is that again the bandwidth is more. I am increasing my bandwidth over the minimum required. What is minimum required? RB by 2. So I am increasing over RB by 2 till RB. This is the disadvantage of Nyquist first criteria, and we will try to cover this through another um, topic, that is Nyquist second criteria, in which this disadvantage has been covered up or has been taken care of. Thank you.